In order to first deal with pyruvate, first it has to enter the mitochondria. Once it enters the mitochondria, then it can actually get into that citric acid cycle, but that's where all of those enzymes are. The very first thing we're going to worry about is that decarboxylation of pyruvate, and that's going to occur through a couple of different things. Oxidative decarboxylation of pyruvate is going to be catalyzed by the pyruvate dehydrogenase complex. So we're often going to refer to this just as pyruvate dehydrogenase like it was one enzyme, but in fact that's wrong. Pyruvate dehydrogenase is actually made up of 3 different enzymes, and they all have slightly different functions. So we're going to be taking a look at each one of these in turn and at the complex reactions required to get pyruvate from pyruvate to acetyl-CoA. In this, 5 different coenzymes are required. Those are thiamine pyrophosphate, lipoic acid, CoA, FAD, and NAD+. In the beginning, so this enzyme is called pyruvate dehydrogenase. The very first step is pyruvate is going to be decarboxylated, and in doing so, it's going to go from pyruvate with 3 carbons to this hydroxyethyl group that is then covalently attached to thiamine pyrophosphate. Thiamine pyrophosphate enzymes typically catalyze decarboxylation reactions of alpha keto acids. Thiamine, also known as vitamin B1, is required for the synthesis of thiamine pyrophosphate. As you might have imagined from the name, all that happens to finish making thiamine pyrophosphate is to have a reaction with ATP where it can then get those 2 phosphate groups to finish that reaction. Thiamine deficiency is what causes beriberi. Once we have our hydroxyethyl group on our thiamine pyrophosphate, we're then going to transfer it onto something else. As the hydroxyethyl group moves from thiamine pyrophosphate for lipoic acid, it's going to be oxidized. So therefore, we're going to stop talking about the hydroxyethyl group being transferred because as it's oxidized, it's then going to form an acetyl group. So then we're going to be calling this new form that acetyl dihydrolipoate, which is essentially that acetyl group attached to lipoic acid. Lipoic acid also is going to come in oxidized and reduced forms. So in order for that 2-carbon unit to go from being a reduced form to an oxidized form, our lipoic acid is going to start off in the oxidized form and it's then going to be reduced by those 2 carbons. That lipoic acid is actually covalently attached to a lysine residue, and we're actually going to see this chemistry again in another enzyme in the TCA cycle. Step 3, we're going to move that acyl group from lipoic acid to CoA so that we can finally have acetyl-CoA. Acetyl-CoA is what will go on to the tricarboxylic acid cycle. So this is looking at CoA, so you'll notice that it has different parts to it. Its 2 main functions are to have that activation of acyl groups so they can be transferred by nucleophilic attack, so it's going to help those 2 carbon units get into the TCA cycle. It also helps to activate the alpha hydrogen of the acyl group for abstraction of a proton. That pantothenic acid that's found in CoA is also known as vitamin B3, and so vitamin B3 is what goes into the making of coenzyme A. This is simply looking at how having that coenzyme A attached to those 2 carbons is going to make those 2 carbon unit better for nucleophilic attack and the next reaction down the line. It's also going to make the reaction overall more favorable. So as you look below, you see 2 different reactions, one using acetyl-CoA and one just using ethyl acetate. And between the 2 of them, you see a much larger negative delta G value when acetyl-CoA is utilized. The steps previously that involved lipoic acid were all the E2 part of the complex. So when we're looking at this diagram, we realize that there was that pyruvate dehydrogenase that involved thiamine pyrophosphate. Then we have another enzyme that is the second one, which is this dihydrolipoyl transacetylase. This enzyme then has the lipoic acid as part of it. At this point in the process, we've gone ahead and we've dealt with that acyl group. It's already now attached to CoA and it's on its way. But what we need to do now is our enzyme that has lipoic acid is not yet ready to react again. Right now our lipoic acid is in its reduced state, and so that needs to be reoxidized so it can continue the process. In order to reoxidize that, we're going to need to reduce something else. So here in our last enzyme, the dihydrolipoyl dehydrogenase, also known as E3, is going to have a flavoenzyme, and it's going to go ahead and take those electrons, reducing FAD to FADH2. Then it will also, in order to reset itself, use NAD+ to go to NADH. that last enzyme, that last dehydrogenase, is essentially doing two different oxidation reduction reactions. NAD plus NADH is something that we've looked at before, but just to remind you, now that we're going to get more into electrons, one of the things to remember about NAD plus NADH is that it can hold two electrons. So when it does go ahead and take on that hydride, it is going to be able to work in two electron transfers. FAD, on the other hand, actually has multiple oxidation states. So the FAD-FADH2 complex has three different oxidation states, and so it can actually do either one electron transfers or two electron transfers. This is why you often have these flavoproteins catalyzing lots of different reactions in biological systems, because they can work with a lot of different donors and acceptors of electrons. So now that we've looked at everything close up, it's time to kind of take a step back and remember that these are three different enzymes. So the pyruvate dehydrogenase, using thymine pyrophosphate, the E2 enzyme, which has lipoic acid and is going to also be trading things off to CoA, and E3, which is going to have FAD as part of the enzyme itself, and is going to use NAD plus then as another factor to do that final step. Pyruvate dehydrogenase complex is actually really interesting because it's not just one big complex that has those three different enzymes in it, but it is one kind of enormous enzyme. The exact stoichiometry of this does depend on the species. In E. coli, the core is made up of 24 subunits of E2, then surrounded by 24 subunits of E1, and then 12 subunits of E3. So as you look at this, there's essentially an inner grouping that has the E2 complex in it, which that's the one with the lipoic acid. Then once you have that inner grouping of the lipoic acid units of the E2, on the outside of that then go the E1 subunits, that pyruvate dehydrogenase. And then in and amongst those E1 subunits, kind of still on the outside, will be the E3. So when you're looking at this, again, E2, which here is shown in green, is the one that's actually farthest in the inside. It should make sense that the one that's going to accept the substrate in the very beginning is more on the outside. So that pyruvate dehydrogenase, E1, is more on the outside. It's going to accept pyruvate. And then as it transfers that hydroxyethyl group to lipoic acid, the lipoic acid is actually essentially going to swing around. That lipoic acid actually has a lot of movement and is going to physically move that group away from E1 to CoA, and then that group is going to actually keep moving so that it can go ahead and be reoxidized to start everything over again. So that lipoamide is that swinging arm that allows it to visit all three enzymes. And again, a reminder that that thing that's going to help reoxidize that lipoic acid is going to be that E3, is going to be flavoenzymes, since it has that FAD with it.